Okay. All right. So the intro to chapter 3 is just that, many systems you can't find the solution to, but linear systems you can. All right. So the harmonic oscillator was derived by taking force is equal to mass times acceleration from Newton's laws. Then when you apply it to a mass spring system, you get this second order system. Hooke's law. This is all re-derivation stuff we already done. Okay, then you end up with this first order system. Okay, so this is the second example of just the matrix equation. Okay, then they showed two different parameter settings, or two different parameter settings. You can get purely oscillatory behavior, and you can get decays to 0. Right, since it's the daily profits, okay. Then it's break even. Okay. They give it a name. Okay, new notation. All of this is pretty simple. A couple examples. Okay, we understand that. Y of t and dy dt. Okay, A is called the coefficient matrix. All of this should be like pretty second nature. Okay, defining dimension. Okay, equilibrium points. Equilibrium points is like a direct application of basic linear algebra, it seems. First off, if you're always going to get 0, 0 as an equilibrium point. But also all solutions to the homogeneous linear equation. That's the trivial solution. Okay, but then you can solve the system of linear equations. Okay, so then they describe the determinant of a 2 by 2. And remember, the determinant is really like, for me, it's a geometric thing, right? It's like if you have n vectors and you want to figure out what the volume of that thing is tracing out, and that's why the determinant in 3 dimension is so hard to understand. But in 2 dimensions, it's not so hard. Okay, yeah, this is a basic application of I guess of linear independence and the invertible matrix theorem. Okay, then they bring up the word degenerate or singular. Okay. All right, then they show that there's an if and only if. If you have non-trivial solutions to the system of equations, then the det must be 0. They give a proof? I don't know. Okay, so the linearity principle is that you can scale solutions and you can add 2 solutions together and you'll still be, I mean, basically the idea is that the solutions of the linear system forms a subspace. And so, then you get all of the vector space stuff called the principle of superposition. Okay, so taking together, the 2 parts say that, so this is the solution of the form is called a linear combination of the solutions y1 and y2. In section 2.4, we found this system had a solution. Now, the whole thing that there's 2 possible solutions is pretty interesting. Okay, you could practice if you want. The solution curves for y1 and y2 are shown. Note that each one is a line segment. The solution curve for y1 approaches the equilibrium point as t goes to minus infinity. And the solution curve for y2 approaches the equilibrium point. Wait, is that true? Wait, how does this one approach the... Oh yeah, of course. It's the exponent. If the exponents are negative, then it is. Yeah. All right, I was getting confused. Yeah, that will decay. But then this one, since this is positive, it doesn't decay. Okay. Okay, to illustrate this fact, we directly check that a linear combination of the two solutions is also a solution. So they get this, then they compute its derivative, then they multiply this by the matrix, and then they find that it's a solution. Okay. We emphasize that solution curves for the solutions y1 and y2 possess a very special property and useful geometric property. The fact that they form line segments is not typical of solution curves in general. In fact, the typical solution curve of this system is not a straight line. For example, as we've seen, the solution of the curve y1 plus y2 is not straight. Right. Doesn't it go to the other side, though? I'm pretty sure it also goes to the other side. So you have like these two lines that trace out the space. All right. To show that the linearity principle holds in general, we first state two algebraic properties of matrix multiplication: scalar and distributivity, and verify these two facts for 2 by 2 matrices of two-dimensional vectors by direct computation. All right. All right, so you can verify using the standard rules of differentiation. Suppose that okay, then they do a basic proof. Okay, so the linear combination is called the two-parameter family, since there's two parameters that you can adjust. To see how the linearity principle is used to solve initial value problems, we return to a differential equation discussed earlier. Suppose we want to find the solution yt with the initial value 2 minus 3. We already know that or solutions. Okay, so then you solve. Oh, okay, so you take y 1 0 and y2 0. You form a matrix, and then you have ax or a system, either way you want to put it. But then you solve that for the. So you solve ax equal to the initial condition. That's pretty simple. Makes sense. Okay, by the linearity principle, we know, and the uniqueness tells them this is the only function that solves the initial value problem. All right, great. So the solution has all the properties that we want in that it is a solution and it's unique. In this example, we found that the solution to the IVP using the two solutions that were already available to us. Maybe by taking the appropriate linear combination of two known solutions, we were able to find a solution with the desired initial conditions. Maybe we were just lucky. Will we always be able to find the appropriate K1 and K2? To check, suppose we have the same differential equation with arbitrary. The second equation is so simple, we can always find K1 and K2. Okay, so basically, since this spans the space, but I don't. Yeah. Expressing arbitrary vectors as linear combinations of given vectors is a fundamental topic in linear algebra. In the two-dimensional case, the key property that ensures an arbitrary vector can be written as some linear combination of the other is that they do not lie on the same line through the origin. We say that the two vectors are linearly independent if they do not lie on the same line through the origin, or equivalently if neither one is a multiple of the other. Yeah. So if they're independent, then they span the space. That's fine. The previous example and theorem illustrate the way in which we approach every linear system. Suppose y1 and y2 are solutions. If y1 and y2 are linearly independent, then for any initial condition, we can find constants k1 and k2 such that the linear combination is a solution to the IVP. In this situation, we say that the two-parameter family is the general solution of the system. By existence and uniqueness, we know that each initial value problem for linear system has exactly one solution. Given any two solutions of a linear system with linearly independent initial conditions, right, the initial conditions need to be, we can form the general solution of the system by forming the two-parameter family. By adjusting K1 and K2, we can obtain the solution that satisfies any given initial condition. We now know how to find all the solutions to a linear system. We need to find only two particular solutions with linearly independent initial positions. So two solutions of a linear system for which y1 of 0 and y2 of 0 are linearly independent are called linearly independent solutions of the linear system. In the exercises, we will see that y1, y2 are solutions of a linear system and linear at any particular t, then they're independent for all values of t. Well, that's interesting. The next step is to find. Yeah, I mean, I feel like that's actually kind of obvious, but that's pretty cool. The next step is to find a general way to come up with two linearly independent solutions. Okay, so 3.2 and 3.4 shows how to do that. All right, an undamped harmonic oscillator. Okay, write it as a matrix. Recall the second component of the vector field. You can use the solution y1. What are they doing here? Okay, they do this, and they do this, and they show that that is a solution. And then they have another solution, which is just sine cos instead of cos minus sine. Okay, so then they find the general solution to the undamped harmonic oscillator. That's chill. But wait, recalling that the solutions are really functions of the form where y of t is a solution, we obtain the general solution as it's only the top. It doesn't, because this is just the derivative. So I guess that's important. All right. Time to do some problems. You gotta get hydrated, bro. I gotta go make some coffee. Okay, let's do some problems. Suppose A equals 1, C equals -1. So what did we have? We had this was 1, this was -1, this was 1, and this was -1. Okay. And this is 2 -1, 0, 0. These solutions are so silly because it's like, okay, if on the first day you lost money, then you're just gonna lose infinite money. Okay, 1, 0, 2, 1. 1, oops. 1, 0, 2, 1. Okay. Okay, 5 through 7, we don't really need to do this. Write it as a matrix form. They're just checking that you know syntax, but I mean, come on. It's pretty easy. In component form. Okay, that's also pretty easy. Okay, here. Okay, we can do this one. 2, 1, 1, 1. 2, 1, 1, 1. Okay, so if we're at 1, 1, we're just gonna go that way. And if we're gonna, let's just, I probably should be better at just like recognizing what the eigenvalues are, but we'll just start this up and see if we can't just. Is it 2, 1, 1, 1? Let me just look at I think it's just called eigen, right? Yeah. Because it looks like it's like the two eigenvalues. It looks like they're both positive. Well, they're definitely both positive. But it seems like it's that line and this line. But I don't know what it actually is. Okay, well, while we're waiting on that crap, let's just keep going. So this one, 1, 2, minus 1, minus 1. It is pretty cool watching this change. Bro, what? All right. Okay, 14. Let A be a non-singular matrix. Show that if A equals 0. Okay, so AD minus BC. If A is equal to 0, then these can't be 0. That's obvious. All right. It's just applying the definition of determinant. Suppose A equals 0. Use the result of part A to show that the origin is the only equilibrium point. I mean, you don't even really need to suppose A. I mean, it said A is non-singular, so therefore it's invertible, and it spans R2, and you get all the good stuff. You know, it's independent, whatever. Yeah, right. So it's the origin. Okay, 15. Let it be non-zero. That is, suppose that at least one of its entries is non-zero. Show that if the determinant is zero, then the system has an entire line of equilibria. Okay, so if the determinant is zero, then if the determinant is zero and A is non-zero, then D is zero for sure, and either C or B is zero, or both, and we'll do this one. I haven't gotten a chance to use the camera in a long time. All right. So the question is, A is equal to A, B, C, D is non-zero. But det of A is 0. And what do we need to show? We need to show that there is a line of equilibria. Okay, so the way we can do this is if A is non-zero, then by AD minus BC equal to det A equal to 0, D is equal to 0, and B or C is equal to 0. Okay, so we can then rewrite this as like A 0 0 B or let's say C, I guess, and then A B 0 0. So in this case we have a line. Let's just like draw it like this. Let's say this is like AC. But then in this case, we really only have like a line like this. And so this could be A and this could be B. So here, this is the span of our solutions here, and then just the x-axis is the span of our solutions there. And it's saying, show any point x0, y0, such that x0 is equal to minus b over a, y0 is equilibrium point. Okay, so okay, so in this case, all right, we could just pick values of x and y, right? So if we have like, let's just say 1, 1. Wait, no, we can't pick both of them. We have to pick one of them. So if x is 1, if x equals 1, then y0 is equal to minus b over a. So x0 is right here. But b is 0. B is 0. So that's fine. And then here, oh wait, b is not 0 though. Let's say b equals minus 2 and a equals 1. Then y0 is equal to minus 2. But that doesn't make sense. All right, so you pick a value of x2. Let's pick y is equal to 1 and x is equal to minus b over a. Yeah, I mean, I understand the linear algebra of this. I just don't, like, know exactly what they are talking about with. Because, okay, if you had, like, A, B like this, then let's say, like, A equals 1, B equals 2. So this is, like, 1, 2. I don't know. Wait, no, I thought we assumed that A is 0. Okay, whatever. I just like the linear algebra argument that, okay, since the determinant is 0, and it's non-zero, then the null space is one-dimensional. That's just how I would answer it. All right, we can move back. That's how I would answer that. Okay. I'm not doing this. This is boring. It's just going to be the same as they had up above. It's going to be it's going to be 0, 1, PQ, I think. Or no, it's going to be 0, 1 minus P. All right, let's just do it. Okay. Let's just do it. Why not? All right, so this is problem 16. So we have y double prime plus p y prime plus q y is equal to 0. Right? First order matrix form. Okay, so we're going to get y prime equals v, v prime equals minus p v minus q y. So in matrix form, we're going to get dy dt is equal to 0, 1 minus p, or minus q minus p times yv. All right, so that's that one. Now it's saying, so for part B, show if q is not equal to 0, then origin only fixed point. So this is obvious because if this is non-zero, then you have two independent column vectors, and therefore it spans the space. Show that if q is not equal to 0, then the only solution with y constant. Okay, so then it's the same. It's like, okay, so for this, show if q not equal to 0, then 0, 0 only fixed point. And this is because since it's linearly independent, it spans the space, and thus, if you have something that spans the space, then the only, that's homogeneous, then the only solution is the trivial solution. So that's that. All right, so that problem was really easy. All right. Consider the linear system corresponding to the second order equation. Okay, if Q is 0 and P is non-zero, then you're going to get the matrix 0, 1, 0, minus P. So then you're going to have some, line. You're just going to have some line. It's not even that interesting, man. Okay, now every point is an equilibrium point. Wait, is that true? No, if Q and P are 0, then the span is just going to be 0, 1, 0, 0. So then you're going to have the x-axis at your disposal. Okay. Consider this. Convert it into first order. Find the general solution. Okay, we could do that one. General solution of that. What is that going to be? So you're going to have y prime equals v, v prime equals 0. So then the matrix is going to be 0, 1, 0, 0. So just like we had, right? So then we're going to have dy dt is equal to v. So dv dt is equal to 0. So it's just going to be plus c, right? V is equal to c for the integral. So then y is equal to vt plus c. Or that's y prime, right? No. That's y. So it's just going to be velocity times time plus some constant for the initial position. So I'm pretty sure that that's that. Substitute this into the... Oh, and find the... Okay, so then if we take the derivative, we get just v is equal to y prime. And then you're good. And v is just equal to v. Sketch the phase portrait. I don't know about that. But just double check the first two. Yep, that's what I got. That's what I got. Oh, well, I didn't actually write that, though. Because v equals c, so this would be c1 plus c2. T plus c2. Okay, that makes sense. So that's y. So then the vector form... Yeah, T1, that makes sense, plus C2 times 1, 0. Yep, okay. There must be a way to do that. You got to go d y of t y5 like that. That's not. Oh no, because you need to do t. Okay, that's what I thought. All right, so then you want to do this. Then you want to say is equal to 0. Then you want to convert it to first order. How do you convert it to first order? There's got to be a way to convert to first order. First orderize? Is that a real thing? How do you use it? That's not what you want. Isn't there a guide page? I want to first orderize. The input signatures of all three functions are the same. First argument is the set of equations. You have to provide the set of states, though. How silly is that? What? I just want a matrix, bro. What if I type in first orderize? Do I have to do some weird import thing to like use this? I don't know. Takes 4 to 6 arguments? What the hell? How do you use this? Okay, so it's harder than I thought. Whatever. I don't know why I'm getting hung up on that. I just kind of wanted a matrix, but that's fine. I don't even really freaking care, man. All right. In exercises 20 to 23, we consider the following model of the market for single-family housing in a community. Let S of t be the number of sellers at time t and b be the number of buyers at time t. We assume that there are natural equilibrium levels of buyers and sellers, people made up of people who retire, change job locations, or wish to move for family reasons. The equilibrium level of sellers and the equilibrium level of buyers. However, market forces can entice people to buy or sell under various conditions. For example, if the price of a house is very high, then house owners are tempted to sell their homes. If prices are very low, extra buyers enter the market looking for bargains. We let B of t equal B of t minus B0. Denote the deviation of the number of buyers from equilibrium at time t. So if B of t is greater than 0, there are more buyers than usual. We say that it's a seller's market. I don't know what that means. Presumably, the competition of the extra buyers for the same number of houses for sale will force the prices up. Similarly, we let S of t be the deviation from the number of sellers. So if there's more sellers, if S of t is greater than 0, there's more sellers on the market than usual. If the number of buyers is low, then there are too many houses on the market and prices decrease, which in turn affects decisions to buy or sell. Okay, the exact values of alpha, beta, gamma, and delta depend on the economy of a particular community. Nevertheless, we assume that everybody wants to get a bargain when they're buying a house and to get top dollar when they're selling a house. Then we can hope to predict whether the parameters are positive or negative, even though we can't predict their exact values. If there are more than the usual number of buyers competing for houses, we would expect that price of houses to rise, and this increase would make it less likely that new potential buyers. What does this say about alpha? Um, so if B is greater than 0, then there's more buyers than its natural equilibrium, and we expect the prices to rise. So we would expect that alpha is negative, I believe. Okay, so for 20, so alpha must be negative, I think. If there are fewer, so that means that B is negative, then we'd expect the price of houses to decrease. And so B is negative here. So gamma is going to be positive. Okay, so my expectation is alpha is negative, gamma is positive. Consider the effect on house prices if S is greater than 0. Okay, so if there's more sellers, then there's a race to compete for buyers, which means that so S is greater than 0. So that means that there's a surplus, so then buyers will grow. So beta is positive. And delta is I think delta is going to be negative because imagine that there's a ton of buyers and there's no sellers. Or like, less than equilibrium sellers. So this is S is negative. So then the growth is going to be really high. So delta is negative. Okay, 24 show that that's boring. Maybe we'll do this just for the initial value problem part. All right, let's do it. Okay. All right, so the problem is y prime is equal to 2011 times y. Show y1 of t equal to 0 e to the t and y2 of t equal to e to the 2t, e to the 2t are both solutions. All right, so the first one, we're just going to compute dy1 dt is equal to 0 e to the t. So it doesn't change at all. Okay, so now we want to show that this is equal to 2011 times 0 e to the t. So this is going to be equal to this is going to be 2 times 0 plus 0 times e to the t. Wait, did I write this down wrong? Okay, then it's going to be 0 times 1 plus 1 times e to the t is equal to 0 e to the t. So that's a solution. That one's easy. Okay, then the second one, dy2 dt is equal to 2e to the 2t, 2e to the 2t is equal to 2011 times e to the 2t, e to the 2t is equal to 2 times e to the 2t plus 0, and then e to the 2t plus e to the 2t. Therefore, we're good. Okay, so what that means is that our general solution is going to be equal to k1 times 0 e to the t plus k2 times e to the 2t e to the 2t. Okay, so now if we want to solve, so this is part B, solve IVP of y0 equal to minus 2 minus 1. Okay, so first off, wait, actually, is this right? I think that this is right for the general solution, but we want to solve y1 of 0 is equal to 0, 1, and y2 of 0 is equal to 1, 1. Okay, so then we need to solve the system 0, 1, 1, 1 times x is equal to our initial value problem, minus 2 minus 1. I think. So the augmented system is, we can rewrite this as 1, or no, wait, we can't. Wait, this is minus 1. So this is really going to be K1, K2, right? Oh, wait, what am I talking about? Why am I being so stupid? So yeah, so K2 is equal to minus 2. So then we're going to get K1 minus 2 is equal to minus 1. So then K1 is equal to 1. So then for the IVP, we're going to get y of t is equal to all right, that was actually pretty fun. All right, so switch back over. Do we want to do this one? All right, we'll do that one. That one seems kind of fun. It seems fun because there's like a product rule in there, and it seems a little bit weirder. All right, so let's just set it up. y prime is equal to 1 minus 1, 1, 3 times y. Then we get show y of t equal to t e to the t and minus t plus 1 e to the 2t is a solution. Okay. All right, so okay, so this one, so for the first thing we want to do is we want to compute dy dt. So we're going to get, so we have t e to the t, then that goes going to go to e to the t plus t e to the t. And let's just do minus t minus 1 times e to the 2t. That's going to first turn into minus t e to the 2t minus e to the 2t. And that's going to, under the action of d, is going to be, it's going to be minus e to the 2t plus minus t e to the, or 2 t e to the 2t. And this is just going to be minus 2 e to the 2t. Okay, I think that's right. So anyways, then we just need to figure out that to do e to the t plus t e to the t. So this is 1, so we're doing the matrix product now. So this is going to be minus 1. So this is 1 times that minus 1 times, so the full thing is minus e to the 2t minus 2t plus 1 e to the 2t. Okay, so what cancels? No, there's too much algebra. It's too much algebra for me, man. Let's see. So then this just becomes plus e to the, oh wait, I did this wrong. No, I did this wrong. Okay. So what we're trying to get is we have dy dt on the left side, which is going to be e to the t plus t e to the t. And then this one is going to be minus e to the 2t minus 2t plus 1 e to the 2t. Something like, I think that's right. Let me just do a quick check. So this is going to be, what is it? It's, yeah, minus t plus 1. God. Oh my gosh. So annoying. Okay. So it's, yeah, minus 2. Okay. Minus e to the 2t plus 2e to the 2t minus, okay, great. So that's correct. So now all we have to do is say that that is equal to 1 minus 1, 1, 3 times t e to the t minus t plus 1 e to the 2t. So then we're going to get, so for the first one, we're going to get t e to the t Wait, this seems wrong. Oh, wait, that's because I wrote this down wrong. This is a 2t here. So then this derivative is wrong, because this needs to be e to the t plus 2t. Okay. So then this is there's a 2 there. So then there's a 2 there. Okay, so maybe now we're a little bit closer. This is t e to the t. That's going to turn into a plus. So then you're going to get t e to the 2t plus e to the 2t, which is equal to 2t e to the 2t plus e to the 2t, which is, oh, and wait. This is also going to be a 2. This is going to be a 2. All right, so that's correct. All right. So that's good. So then the second one, it's just more algebra. It's like, whatever. Let's just move on. All right, so for 26 to 29, two functions and an initial value are given. For each system, check that the two functions are our solution. Check that the two solutions are linearly independent. Find the solution to, okay, these seem kind of fun. Okay, so all right, so let's just try to do it symbolically. I'm faster with Julia, I think. So A is equal, what is it? Minus 2, minus 1, 2. Minus 1, minus 2. What was it? Oh my gosh. 2 minus 5. Oh, wait, how do you take the derivative again? What? Dude, that is insane. It doesn't even do it. What? Wait, why doesn't it actually compute the derivative? Dude, their symbolic programming is just so garbage. All right, let's just do it like this. I just don't like typing in this, though. It's just so clumsy, I feel like. Okay, so we have y1 is equal to, let me just write it down on paper and then I'll do it. So we have, for 26, we have y1 of t is equal to e x minus 3t, x minus 3t. Okay, a is equal to minus 2 minus 1, 2 minus 5, and y2 is equal to x minus 4t, 2e minus 4t. All right. Surely this will work. Oh, you know what we need to do? Okay. I think it's fine. Oh, you know what? Whoa, that's so weird. Oh, that's so weird. See, that's the thing about their syntax. All right. Yeah. There we go. All right. So the second one is exp minus 4t, 2 exp minus 4t. Okay, now we can just do dy1t. Nice. Is equal to okay, then let's get a is equal to list of lists. It's going to be minus 2 minus 1. I feel like it's just so verbose. That's the thing that's nice about Julia in this regard. Ugh. Okay. So this should be a times y1. AY1 should be a vector. I don't see what's happening here. You know what? I think you have to do like a dot. Maybe you have to do like a, yeah. Cool. And then we can just do this for y2. And there we go. All right, so we just showed that that indeed it is a solution. So now check that the two solutions are linearly independent. Okay, so if we were to factor this, um, y1 of 0 is going to be equal to 1, 1, and y2 of 0 is going to be equal to 1, 2. So is that what they mean by checking that the... Can't I just okay. Let's see if okay. Right. Right. All right. It's cool. But we need to find the we're not done with 26. Okay, so now we have was it 2, 3? So we want to do can we do this? All right, so there we go. So K1 equals 1 and K2 equals 2 or 1. $27. What a pile of algebra, man. I'm not doing that one. Oh, the Ronxian. I'd never heard of this before. Pretty interesting. Yeah, I'll be right back. All right. Okay. All right, let's do this. So which one were we actually doing? Because I feel like I skipped over too many of them. Yeah, we get the idea here. It's just a ton of algebra. Then this, um, yeah, you just get like yeah, you get A11 times KY1 plus A12 plus KY2. You can factor out of that, then you can factor out of the other one. It's that one's easy. Okay. For which of the following initial conditions can you give the explicit solution? I think it's only gonna be this one and this one. I think it's gonna be A and D. A and D, bruh. Oh yeah, you get C as well, right? I was debating C, but you get C. Okay, this is a good one. 34 is a good one. Okay, so let's just do it. All right. So dy dt is going to be equal to 1 and t. I'm going to check that. So then so dx dt is equal to 1. That's fine. But then, okay, then we get x is t, right? So x of t equals t. So then this is going to be 1t. So we verified it. That's good. Now part B is show 2y of t not a solution. So this shows basically that this system is not linear. So 2y of t is equal to 2t t squared. Okay? So d of 2y is going to be equal to 2t is going to be equal to 2 and 2t, which is equal to 2y prime. Anyways, so there we get that. And now what we want to show is that this is a solution to this same differential equation. So it's not. It's not, because 2 is not equal to 1. All right, that's that. And go back. All right, 35. Given solutions y1 and y2, define the Ronxian of y1 and y2 to be the scalar function. It's the determinant of the two solutions. Okay, compute dw dt. All right, fine. We'll do that. Do that really quick. It's not going to take that long. So we have y prime is equal to ay, where y1 is equal to x1, y1, and y2 is equal to x2, y2. Okay, w is the Ronxian is equal to det of y1, y2. Okay, so dw, which is equal to x1, y2 minus x2, y1. dw is going to be equal to, going to have x1 prime y2 plus y2 prime plus times x1 plus, or this is going to be a big minus, x2 prime y1 plus x2 y1 prime. I don't know what that's supposed to show me. Okay, we're supposed to show that dw dt is equal to a plus d times W of t. Okay, so dy dt is going to be equal to ax plus by, and this is cx plus dy, like that. So that's the whole form, the vector. So what they're trying to say is that if we have a plus d times x1 y2 minus x2 y1, that's going to be equal to this? How's that possible? I don't even get that. What does that mean? Oh, because x1 prime is going to be equal to well, okay, because that's the question. What is dx1 dt? Is it not? Is it not going to be a plus b? I think it is, right? So if we have so if we have okay, so dw dt is equal to x1 prime y2 plus x1 y2 prime minus x2 prime y1 plus x2 y1 prime. Okay, and then what we're saying is that this is supposed to be equal to a plus d times w of t, which is the Ronchian, where w of t is equal to x1 y2 minus x2 y1. That's the Ronchian. So and this is for y prime equal to a times y. A is equal to a, b, c, d, and so then we get y prime is going to be equal to ax plus by, a cx plus dy, right? That's the whole thing. But The thing about that is then if we have like x of dx dt is going to be equal to ax plus by. So if we take the derivative of, is it not going to be, okay, I need to ask. I don't know. Or wait, x1 prime should be, right. Okay, yeah. So no, so x1 prime, okay, that makes sense. So if we expand this big thing out, big thing, we're going to get dw dt is equal to ax plus by times y plus x times c. Well, I guess, do we have to keep track? This is going to be x1, y. Wait, how could you possibly keep track of that? This should be y1. And this is y2. This is x1. This is going to be cx1. Wait, I don't even know. That doesn't even make sense. Okay, all right. That was good. Okay, so that's the start of linear systems.